during the discussion immediately after the lecture, so I want to clarify that. So, in general, we have that if so if A is greater than or equal to B in this Loebner order, so this is the order on partial order on PSD matrices, right. So this, just to write it formally, this is called the Loebner order. This is on PSDs. So this implies that lambda I of A is greater than or equal to lambda I of B for all I, right. So here what Rekha said we wanted to prove was that the second eigenvalue of the Laplacian with these weights is greater than or equal to 1. So that does not, I mean, and then after some argument we came to the conclusion that we should look at this, I mean we should look at all W such that LW is greater than or equal to I minus 1 by Ng. So in general the implication would only be this implies this, right, because of what she just said and I repeated, right. So, but in this case something nice happens. So here Rekha had written all the eigenvalues for I minus 1 by Nj and for LW, right. So that's 0 and all ones, and here it's 0 lambda 2 up to lambda n, right. So the important thing is that the eigenbasis for LW is also an eigenbasis for I minus 1 by Nj, okay. So that's the important thing. So the all ones vector gives eigenvalue 0 for both, right. So we have that all ones vector. Now if you take something in its ortho complement, there is something orthogonal to it, because this is all ones, so it acts as the this I minus 1 by Nj acts like an identity matrix on that subspace, okay. So everything over there is going to be an eigenvector, okay, is that clear? Because it's all ones, it's, I mean you have just taken out the part of the identity which gave you this all ones, so that's to be treated separately, but other than that we have everything else. So in particular all the other eigenvectors of LW are also eigenvectors of I minus 1 by Nj, okay. Not the other way around, because here this is a very fat eigenspace. If you choose some linear combination of things here, I mean if you choose some linear combination of eigenvectors here, that will also be an eigenvector for this guy but not for LW, right. So since this is much finer, this has, so they have the same, they share at least one same eigenbasis, that is the eigenbasis of LW. Therefore these two are equivalent. So if A and B share an eigenbasis, and lambda I A is greater than or equal to lambda I B for all I, okay, assuming symmetric and all that, let us say A and B are symmetric and share an eigenbasis, and lambda I greater than of A is greater than or equal to lambda, then we also have the other way inclusion, okay. So this will hold if the eigenbases are the same. If not, I mean the problem only arises, the converse fails only when they do not share the same eigenbasis. So that is one of the problems. So if you look at problem 3, we are asked to find a counter example to this converse statement, and the problem will come, you will see very soon that the problem will come when they don't have the same eigenbases. Okay. So we'll tackle that in a second, but this, I mean, there was some confusion about this point when we were discussing it, so we thought we should explain. Any questions about this? Okay. All right. So shall we do the, okay, so you have a solution for the sphere as a, disk, yeah. So 2 by 2 matrix example you have, do you want to show it on the board? Okay, so now we are doing this problem. Oh right, yeah. So the exercise was to show that xy such that x square plus y square less than equal to 1 can be written is a spectrahedron. So what is your solution? So we want to write it in the form of some matrix, 2 by 2 matrix. So you want to tell me what the entries? Sorry? 1 minus y, 1 plus y, x and x. Okay. So, no, but this is, determinant is that, but you want to, this means both of these also have to be, because y is greater than equal to minus 1, okay. So, yeah, so let's just write, so the minors, the principal minors are 1 minus y greater than equal to 0, which means y is less than equal to 1, 1 plus y greater than equal to 0, which means y is greater than equal to minus 1, and the determinant is 1 minus y square minus x squared is greater than equal to 0, which is what we want. Okay, yeah, nice. Okay, so this is a 2 by 2, we had a 3 by 3 example, but this is a 2 by 2 example. Okay. Okay, so now we want to, so shall we do the problems in the day 4, from day 4 of the exercise sheet? So the first thing is to argue that the feasible region, or is it spectrahedron, are they the same thing?
The feasible region of an STP,
yeah,
which is
yeah, it's spectrahedron, yeah. Yeah, so we want to argue, so problem 1, f which is x such that
this combination, this LMI is negative.
Yeah, so a of x is convex. So did someone do it already? Someone wants to try it? So you want to take 2 points in this, so let's maybe write this. So this is a0 plus x1 a1. I'll write the xi's this side because otherwise I tend to think of it as matrix times a vector, plus xm am. So this as a matrix is PSD, but we have shown, we have already discussed that the space of PSD matrices is convex. It's a cone. So that should help. Sorry? No, that is a cone. But here we are we are varying over these xi's.
Kind of can you use the convex combination with alpha x plus beta y, which is a of that is less than or
Yeah.
equal to alpha times ax plus beta times a y. So the convex combination of
Yeah, so suppose x and y belong to f, right? So, and let us say alpha is in 0, 1. So, we want to look at alpha x plus 1 minus alpha y, right? So, what would this mean over here? So okay, so maybe before I go there, I can look at the implication. So x and y belong to f. So that means a0 plus x1 a1 plus up to xm am is greater than or equal to 0, and a0 plus y1 a1 plus up to ym am is greater than or equal to 0. Now what? Now if I add alpha times this, if I multiply this by alpha,
you're not multiplying that by alpha, right? It's alpha x. Only the first term a naught will not be multiplied by alpha.
yeah, no, relax. We are coming to that. And if I multiply by 1 minus alpha, let's just see what happens. So what happens? So I'll get alpha a naught from here, and what will I get from here? 1 minus alpha a naught. If I add them, I'll again get a naught. Okay? Plus alpha x1 plus 1 minus alpha y1 a1, yeah, plus up to alpha xm plus 1 minus alpha ym am. So we know this is so these are two PSD matrices. So this is PSD by convexity of this space. What was it? S n up n plus, right? So plus, right? Yeah. So we showed, or we roughly argued that this is convex, right? So you can do this by just looking at X transpose. If you have two matrices which are PSD, to show that anything on the line between them is PSD, you can use the quadratic form version of that to argue. Okay. So then this is PSD, but what does that mean? So each of these coefficients corresponds to this is the first coefficient of alpha x plus 1 minus alpha y, this is the second and so on. So that means that alpha x plus 1 minus alpha y belongs to X, right? Okay. Okay, so now we come to the converse of this. Okay, so the second question was about the Schur complement. So we'll assume the Schur complement lemma. The proof apparently is a bit complicated, so we won't do it now. So let us go to the third, the other part of the problem we have already done, we have already discussed it. So let's go to the third problem. So can you find an example? So we want, problem 3. So we've already discussed the first part of the problem, which is this forward implication. This was proved using Courant-Fisher. Now we want to go the other way, or rather to show that the converse is false. So suppose A and B are symmetric. Such that so they are real eigenvalues, and lambda I of A is greater than or equal to lambda I of B for all I. Construct A and B so that A minus B is not greater than or equal to, or A is not greater than. So, a 2 by 2 example should work. So, why don't you try? So, try to come up with two 2 by 2 matrices where one has eigenvalues which are larger than the other, but if you take the difference, it is not PSD. And as I told you earlier, it will fail because they do not share an eigenbasis. So, do not do something silly like taking them to be diagonal matrices or something, it will not work, okay. We have to do something a little more clever. Diagonal will work? No, but you have to order the eigenvalues, right?
Oh, sorry. I mean, this is A and B, they are both, they satisfy this condition.
Okay, fair enough. Yeah, actually you can take them to be diagonal, yeah. So, yeah, so okay, I stand corrected, yeah. Because of the ordering being a problem.
Its determinant is -1.
But no, I did not say just about their eigenvalues. Okay, so she has a nice example. Can I borrow? Yeah. So here's an example. So A is 0, 1, 1, 0. This has eigenvalues 1 and -1. Lambda 1 equals 1, lambda 2 equals -1, and B equals 0, 0, 0, -1. Lambda 1 is 0, lambda 2 is -1. So this, so that's okay, right? But A minus B is 0, 1, 1, 1, which is not PSD, which has well, okay. So it has determinant -1, so it cannot be PSD. So the product of the eigenvalues is negative, so yeah. So some has even simpler example because, so what I said was wrong. So if you take A equal to 1, 0, 0, 2 and B equal to 2, 0, 0, 1, they share the same eigenbasis, but because of the ordering being messed up, so lambda 1, so for both lambda 1 is 2 and lambda 2 equals 1 for both, but because they are associated to different eigenvectors when you take the difference, so A minus B,
Satisfy the ordering condition, right?
they do, right?
Lambda 1 of A greater than or equal to lambda 1.
Lambda 1 both are equal. It's just that
Your eigenvectors
are associated differently. So then A minus B you will get I don't know -1, 0, 0, 1. So yeah, so it's even simpler than that. Yeah. Okay.
But you are ordering them, no?
Yeah, so we are ordering them in whatever you want, increasing or decreasing order, but we are not controlling the eigenvectors, right? We cannot say anything about which eigenvector comes first or anything, right? So,
So you mean to say that this exercise is not true?
I mean the converse is not true. This holding does not imply.
But you put some additional condition.
Yeah, if they, right, so this is also not true, right? So I should correct that.
No, there also if you see the eigenvector associated with 1 is 1 0, right? Yeah.
Yeah, so
A and B here is
yeah, so here the ordering is by,
Sir, I think this is simultaneously diagonalizable, something simultaneously integerally diagonalizable. If that concept comes, then we can.
but that holds for that, no? No, no, so the problem is that here I meant the ordering by eigenvector, not ordering in terms of absolute value. So I meant eigenvector by eigenvector, it should hold. So, I should,
So you mean ordered eigenbasis.
yeah,
The basis should be ordered.
share an eigenbase and lambda I for,
No, I think you
for
will
the,
just write the basis as phi 1, phi 2, phi n.
no, but I'm demanding this condition, right? So I'm saying if lambda, okay, so let me write as Anisa said, so let's call it phi 1 to phi n, right? And lambda I of A greater than or equal to lambda I for each phi I. So lambda I is the corresponding eigenvalue for the eigenvector phi I. Lambda I of A is the eigenvalue of A for phi I with eigenvector phi I, and lambda I of B for similarly eigenvalue for B for phi I, then this will imply, right? Then it's okay. So then we have that A greater than or equal to. So that fails here because E1 and E2 are the eigenvectors. They do share the same eigenbasis, but it fails for the first one. Right? One is not greater than or equal to. Okay, and the fourth exercise is to, oh, this also we did, yeah, this also we did. Okay. Okay, so yeah, thank you. Did you want to show something in mathematical?
Maybe not immediately. I have some things to show though later. I'll just keep it ready. We don't need to show it now. Okay. Let's continue. All right. So I want to start here again. Okay. So we were maximizing lambda 2w. We were trying to find the weights that would maximize the second eigenvalue. We normalize the weights because otherwise if you just scale weights positively, the eigenvalue will keep going up. So you have to normalize, and I want this w to be non-negative. Okay, so this is our problem. So I'm going to write, let me erase this derivation, but the key thing that we decided is that this problem is a semi-definite program, and it is the semi-definite program that you see at the bottom. So let's record it over here. Okay, so this is exactly the problem of minimizing it's exactly the problem of minimizing the sum of the weights. subject to the condition that the Laplacian, the weighted Laplacian, is bigger in this lower order than I minus 1 over nj, and we have w greater equal to 0. And this is a semi-definite program. Okay, so they're not equal, they're equivalent, I guess. Okay, they're not exactly equal, but they're equivalent. Because remember, at some point we had to do this normalization, and we have to scale things correctly. Okay, so that is what we have. We proved it. So now I'm going to make a definition. I'm going to ask the following question. Okay, so for many graphs, if you just take the graph and run this SDP, you will see that the weights that are going to maximize lambda 2 is not the all ones weight, it's some other weight. Okay? But if your graph is very, very symmetric, somewhat symmetric, it should be that the all ones is the best weights. Do you agree? It shouldn't be true that if you like change weights over here somehow and don't change the weights over here, or if you do some random thing, it's going to increase lambda 2. So what we might expect is that if your graph has some structure, special structures, then the unweighted graph is already the best. Okay? So I want to turn this into a question. I want to ask to characterize the unweighted graphs for which all ones is the winner. The all ones weight is the winner. You don't need to add any weights. You don't need to change any weights. Lambda 2 of 1 is already better than lambda 2 of any other weight. Okay? So I'm going to turn this around. So people traditionally in the literature do this maximization. In fact, eigenvalue maximization and minimization is big business in engineering applications. And so people have done this, and you can study the optimization, but I'm going to turn the question slightly. And I'm going to make a definition. I'm going to say that the graph G is lower conformally rigid. And this word comes from geometry. If you're interested, I can tell you later. So it's lower conformally rigid if the lambda 2 of the all ones weight is actually bigger or equal to lambda 2 of any weight that satisfies the condition that W is greater or equal to 0. Okay? So if you allow non-negative weights, then whatever lambda 2 you get is not going to be better than lambda 2 of the all ones weight, which is the unweighted graph.
And subject to mod W, sum of the...
Yeah, so we have to normalize. So let's always assume it's normalized, subject to the, so this is true, and then the sum of the weights, sum of the weights is, we're going to set it to the size of E. Okay, so you do have to normalize weights, otherwise this won't work, right?
Why lower?
Lower, so it's a good question. Because there is an analogous definition of upper conformally rigid. If the last eigenvalue, lambda n of 1, is less or equal to lambda n of W prime, not the same W, but W prime, for all W prime non-negative, also normalized. So the all ones dot W prime is equal to the number of edges, okay? So we are trying to, so in terms of the picture of the spectrum, what we are hoping for is that, okay, here is the spectrum of the Laplacian, and we know that 0 is an eigenvalue, for sure, we know it is. And then there is lambda 2, okay? And then there is, at the end, lambda n. These things are, this is how the Laplacian will look like. So what I would like is that lambda 2 of 1, so let's say this is lambda 2 of 1, this should be greater than lambda 2 of some W, should be greater. But on the other end, lambda n of 1 must be smaller than lambda n of some arbitrary weight, okay? So we're looking for graphs, so the upper and lower together means that lambda 2 is as big as possible and lambda n is as small as possible. So lambda n sort of controls smoothness of the graph, right? It's like the highest eigenvectors are the ones that oscillate widely, okay? So this is not entirely very precise, but it is sort of, you expect, it's a kind of symmetric statement. We want lambda n to be as small as possible, so we want the graph to be as smooth and dense as possible, and we want lambda 2 to be as big as possible, which means that it's very connected, okay? So this has some meaning coming from geometry, because in geometry people like to take manifolds and change the metric on the manifold, and then they want to ask, so on continuous spaces there's the Laplace operator that Anissa knows a lot about. So in graphs we have the Laplace matrix, in continuous situation we have the Laplace operator, which is the second partials equal to 0. So it's a continuous thing. And then people would like to know if you change the, if you like blow some parts up and blow down some parts, blow up some parts, if you change the shape, so you keep the metric the same, then when is the second eigenvalue maximized and the top eigenvalue minimized? Okay, there's no top eigenvalue sometimes, but second one. So it has a sort of geometry background, which is my collaborator is an analyst, Stefan. So that's where the word comes from. I can give you some more. I can show you a picture later. That's better. I can't really explain it too much. Okay. So this is lower conformally rigid, upper conformally rigid. And if both of them hold, we call the graph conformally rigid. Okay. So there are graphs for which the all ones wins for lambda 2 and lambda n. Okay. But notice that it's not the same weight, okay? So we're not asking that, so what we're not asking for, it's not true that lambda 2, so lambda 2 of 1 is less or equal to lambda 2 of w, some w, is less or equal to lambda n of 1, is less or equal to lambda n of w. This is not what we're asking. We're not asking that for the same weight, lambda 2 of w is less than 1, lambda, this is not what we're asking. We're allowed to change the weights here, okay? So it's even stronger. It's saying that if you, so they're kind of independent problems. So this one we can run independently and say, okay, is 1 winning? If 1 is winning, then we are lower conformally rigid. And then independently we run the upper problem. And you ask again, is 1 winning? If 1 is winning, then you're upper conformally rigid. And if both happen together, we call it conformally rigid, okay? So this is a notion that was again introduced in a paper of Stefan and me. So this is Steinerberger. So this is work from last year, I think. Yeah, it was just published, 2025. And so we defined these notions of lower conformally rigid, upper conformally rigid, and also just conformally rigid. Conformally rigid means you have both, okay, upper and lower. And we wanted to know for which graphs is this true, that you are upper and lower conformally rigid, or maybe only one. There's a follow-up paper with Joao Gouveia that also deals with this. Okay, so that is the definition. Everybody okay? So first thing you can ask is there any graph like this, right? Because it's a pretty strong condition that the all one should win from the bottom and from the top, right? Is there any graph like this? So if there's any one graph that you think will win, which one might it be? The complete graph. Okay, so let's argue that the complete graph is lower and upper conformally rigid and therefore conformally rigid, okay? So I'm going to show you one side and then maybe you can argue the other side. So I'm going to argue that the complete graph is lower conformally rigid. And then we'll talk about what kind of application this has. Why is this interesting? So let's argue that the complete graph is lower conformally rigid. So claim is that if you take lambda 2 of the complete graph, okay, so if G equals to the complete graph is lower conformally rigid. Okay, Now we know lots of things about the complete graph, right? We've been computing its eigenvalues for a while. So what is the Laplacian of the complete graph? Yeah, so let's write down the eigenvalues of the, so there's the Laplacian of the complete graph. So remember we computed this some time ago? Yeah, so it should have, the degree of the graph is n minus 1, so there should be n minus 1s on the diagonal, and then everywhere else, just a minus 1, everywhere else, okay? So you can write this as n times the identity minus j. Do you agree with this? Okay, so this is n times the identity minus j. And because of that, we also know the eigenvalues. So what are the eigenvalues? The eigenvalues are 0 at the bottom. And then after that, n, right? So all the other eigenvalues are just n. So these are the eigenvalues of the complete graph, Laplacian, okay? So those are the eigenvalues. So this means that lambda 2 of 1, this is the unweighted graph, right? So this is lambda 2. So this is lambda 2 of the all ones. Okay? So what we need to show is that no weight can have a lambda 2 that is bigger than n. Okay? So we need to show, so we want to show that lambda 2 of any other weight is less or equal to n. Right? N is the second eigenvalue of the complete graph Laplacian. And I want to argue that if I change the weights on the complete graph, lambda 2 will not go over n. Everybody okay with this? Okay, so that is what we need to show. Okay, so suppose this is not the case, okay? So maybe, okay, so suppose there exists a W, non-negative, so it's also weighted and all, I mean normalized, such that, okay, such that, let's write it down, sum of theWij's is the number of edges in the complete graph, which is how much? How many edges are there in the complete graph? N times n minus 1 divided by 2, right? This is the same thing as n choose 2. So all possible edges are there. So the normalization on the weight is that. So suppose there exists a W like this, such that this is true, and also lambda 2 of W is bigger than n. Suppose this happens, okay? So let's derive a contradiction if this happens, okay? All right, so if the second eigenvalue is bigger than n, then what happens to the sum of all the eigenvalues? Let's look at the sum of lambda I W as I goes from 1 to n. The first one is 0. We know the first one is 0, right? So if you start counting from lambda 2, lambda 2, lambda 3, blah, blah, blah. Lambda 2 is already bigger than n, okay? So lambda 3 is also at least n, or is at least as much as lambda 2, and the rest are even more and more and more maybe, or they're all the same, it doesn't matter, but they're all at least bigger than n, right? So can you put a bound, a lower bound? So the lambda 2 is at least n. Yeah, exactly. And all the rest, there are n minus 1 non-trivial eigenvalues. So I know that n times n minus 1 is strictly less than the sum of the lambda i's. Do you agree? Because lambda 1 is 0, so it comes for free. We can add it in. So I get n times n minus 1 is strictly less than the sum of all the eigenvalues, right? But that's the trace of your matrix, right? Sum of eigenvalues of a matrix is the trace of the matrix of the, so this is the trace of the weighted Laplacian. But we know what sits on the diagonal of the weighted Laplacian, right? So we can compute the trace. Remember, in every diagonal entry, it's the sum of all the weights of the edges that touch that ith edge, okay? So let's add it up. So what is the trace? Right, so for each, so if I pick one particular I, then I have to take all the j's that are adjacent to I, and I have to sum up the weights. But then I have to do this for every I. Do you agree? So I fix an eye, add up the weights of all the edges that touch this eye. That's the second term. But then I got to do this over all eye. That's the trace. Okay? How does this compare to this? So this is over just all the edges in the complete graph. It's twice, right? Exactly. So this is equal to, this was n times n minus 1 over 2. So this is equal to n times n minus 1. Right? Now we're done. So we started with n times n minus 1. It's strictly less than n times n minus 1. So that's the contradiction. Got it? So for the complete graph, you cannot have any weight that's going to be better than the all ones weight, strictly better. So it tells you that the complete graph is lower conformally rigid. Do you agree? It's just a very simple argument, right? And in the case of the complete graph, you can also argue, this is not clear from this, that the all ones is the only winner. It's the only maximizer of lambda 2. Okay, every other weight will have a strictly smaller lambda 2. And this in general we don't understand. So if you ask for, it could be that the all ones wins, but many other weights could also win. That we don't mind, right? It could be that lambda 2 of 1 is the same as lambda 2 of a different weight. That's okay. We're just asking that lambda 2 of 1 is nothing else is better, strictly better, okay? But in general, we don't really know for which graphs the all ones is the unique maximizer. For Kn it is, for the complete graph it is, okay? So that's an open question. If we can characterize those graphs for which the all ones is the unique maximizer of lambda 2. We don't know that, okay? So can you argue that this is also low upper conformally rigid? Same ideas. Maybe think about it. We'll come back to it in the next session. Okay, that's exercise, okay? What? How do you get the first inequality? Okay. So the eigenvalues are these, right? So what is happening? Okay, so we are assuming, we're supposing that there is a weight where lambda 2 of that weight is bigger than n. Okay? So that means lambda 2 is bigger than n, lambda 3 is also bigger than n, because lambda 3 is bigger than lambda 2. Lambda 3
exists.
It definitely exists.
N is, we are assuming n is bigger than.
What?
It's a symmetric matrix, no? So
Okay, so maybe let me say it again. So we're taking the weighted Laplacian, LW. It has n eigenvalues. First,
N is the number of vertices of the graph.
correct.
Kn.
N is the number of vertices of the graph.
Assuming that is greater than 2.
Oh, that n is greater than 2? Yeah, please assume all that, okay? These corner cases, I don't know, okay? Think about it. It works. Yeah, n is at least 2. There's at least an edge. Otherwise, we can just go home. Good? Okay. Yeah, there's at least an edge. But,
Strictly more than 2.
why? N into 2 into 1 is okay.
I think it doesn't have to be strictly more than 2, but it should be at least 2 vertices. Yeah.
Stop at lambda 2. Still you get a equal. But that will be equal to
Okay, so
Greater, no? Look at the inequality. There's a strict there.
yeah, I'm assuming lambda 2 is strictly bigger than n. Okay? So then all the other so that means the sum of all the eigenvalues is bounded below by this, right? Because the smallest they can be will be n, but they're probably slightly bigger than n, right? So n times n minus 1 is the lower bound. That's less than the sum of the eigenvalues because lambda 1 is 0, so I can just squeeze it in, and then we continue. It's okay? All right.
So in the last equality,
Yeah,
I remember you compared it with the other one and you said it has to be twice of that,
correct.
right? And that is because the same edge is counted twice.
Twice, exactly. So here we are counting it twice. So
If I is adjacent to j, then j is
exactly. So this wij will be counted when we are focusing on I and looking at j as its neighbor. It'll also be counted when we are focusing on j and looking at I as its neighbor. So this is a double count of the edges. That's why I don't need that divided by 2, but then we get the contradiction. Everybody okay? Okay. So complete graph is there, okay? So that's good. This is not an empty set. The definition is not an empty set. So that is that. And then so think if you can use the same argument to argue that Kn is also upper conformally rigid. It is. It's exactly the same type of argument. You just have to think a little bit. So assume lambda n there's something smaller than lambda n, and then you'll get the same type of contradiction, okay? All right, so there's something in this class, so that's good. So we are in business. So once we have something in this class, yes, so maybe I will make the thingy. Okay, so let me show you some few applications, or at least 1 or 2 applications of conformal rigidity. Okay, so did I define conformal rigidity? So the graph is conformally rigid if it's both upper and lower conformally rigid, okay? So G is conformally rigid if and only if G is, if and only if lambda 2 of W is less or equal to lambda 2 of 1 and lambda n of 1 is less or equal to lambda n of W prime, where W prime and W satisfy these conditions, okay? So that means lambda n is squeezed down as possible and lambda 2 is pushed up as much as possible. Those are these conformally rigid graphs, okay? Great, so Kn is in there.
So Kn is an example where lambda 2 is equal to lambda n.
Yeah, exactly. So this is very, very good, right? So it's really tight, good. Okay, so let me ask you the following question. Suppose you have a collection of numbers, x1 through xn.
In your minimizing summation wij such that NW is greater than or equal to I minus 1 by nj. Instead of saying that, can't we say that LW greater than or equal to LKN? Because that right hand side.
Yeah, it's not quite LKN, it's close, right? This is the LKN is this. So it's 1 over n. Yeah, correct. You can.
So that we can compare with the complete.
Yeah, very good. That's exactly what Lavanya was saying too before. You're essentially, this is essentially the Laplacian of the complete graph up to some scale, right? So yeah, very good point. Yeah. Okay, so let's do a quick high school question. Okay, so I want to look at the following situation. So suppose you have some numbers. So given x1 through xn in the reals, oh, not given. Okay, this is what I want. Okay, let me ask you. So for so given xi minus xj for all I and j, where these xi's are some real numbers, some unknown real numbers. So we don't know the numbers, but we know their pairwise differences. That's what I'm trying to say, okay? So somebody tells you all the pairwise differences of a whole bunch of numbers, but they don't tell you the numbers. Can you recover the norm square of the x vector, okay? Can we find norm x square? Okay, let me ask this question. So norm x square is the same as sum of xi square. So I don't know the number, but there is a vector x, some unknown vector x. Okay, I know all the differences, x1 minus x2, x1 minus x3, all those I know. That means I have a complete graph with all the numbers on the edges. Those are the differences if you want. You can think of it like that. I would like to calculate norm x square, okay? So hopefully you see immediately this is not well defined. Yeah, because I can just arbitrarily add, if I find some collection of x's, and I can just do x1 plus a, x2 plus a, blah, 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 up to xn plus a. I can add arbitrarily something to it. The differences are the same, but the norm is going to keep on increasing, right? So it's not well defined. So I need to add something more. I'm going to also tell you that the sum of the xi's is 0. So I need to like normalize it somehow, okay? So that way if you add stuff, it'll just cancel out when you sum it together, okay? So I also know that this is true. So I've given differences. I know that the sum of the xi's is 0. The question is, can we find the norm of the x squares? Yes?
There was expression for Laplacian, I mean, when we do take the quadratic equation of the Laplacian matrix, then x transpose L k n of x, then we get this kind of expression.
Okay, are you trying to give me the answer? Or it's not a question about the question? No, okay, all right. No, I'm just trying to understand if it's the answer or the question. Okay, so this is the question, okay? So we want something, we're looking for something that connects this information and this information with this information.
This is like one of those Olympiad problems where you write x1 plus up to xn squared into some such thing.
Yeah, I think maybe Aditi was onto something. So this should look like something we've seen.
Yeah.
Courant-Fisher, quadratic form. So, okay, so let's try, okay? So if I claim this is the case, so xi minus xj square, okay, is equal to n times norm of x square. So norm of x square. Rather, let's write it like this. I claim this is the case. Why is that?
Ma'am, if we consider x transpose
Mm-hmm.
Li minus j,
Do you recognize it? It's actually just a one-line answer.
Laplacian of kn, if we consider only that, like Li minus j of x, then we get this n time of norm of x square.
Okay, but okay.
Rayleigh quotient.
It's a Rayleigh quotient of what? Of the complete graph, right? So this is really the same thing as x transpose L, k and x divided by x transpose x. But what's the x that we have to plug in here to get n? Yeah, exactly. Any eigenvector that is perpendicular to the all ones, okay? So if x is 1, so if I evaluate this at x equal to like phi2, the second eigenvector, or phi3 or whatever, then I get exactly the second eigenvalue, right? We know that when you plug in the eigenvector into the Rayleigh quotient, you get back the eigenvalue, okay? So this is really the expression that says that the second eigenvalue of the complete graph, which is n, is the value of the Rayleigh quotient at an eigenvector that corresponds to the second eigenvalue, but every eigenvector that corresponds to the second eigenvalue has this property, right? Sum xi is equal to 0. Okay, so if you have this, if xi minus x, so this is like not a deep fact that I'm telling you. I'm just saying that if I give you these differences, all differences, okay, all differences have to be there, and the xi's have the sum xi equal to 0, which is necessary, otherwise the problem is ill-defined, then you can compute the norm because this is from the Rayleigh quotient, right? This is just the Rayleigh quotient trick. Good. So now let me change the problem. So I don't give it to you for all ij's, but I just give it to you for some ij's. So now the ij's live in the edges of some graph, okay? So I change from the complete graph, I remove some edges, and I only give you some of the differences. And let's assume that those differences are sitting on the edges of some graph, okay? I don't give you all of them. Then can we still do this? Can we find can we find the norm of x square? So it should also be related to Rayleigh quotient somehow. So now in this case, what do we know? So we still know something, right? So the Rayleigh quotient, so this corresponds to some graph. So I know that x transpose Lx for this graph, let's call it Lg, divided by x transpose x. This is the Rayleigh quotient. So we can even take, okay, so let me write it like this. So this is equal to the sum of xi minus xj the whole square over all ij in E. Okay, this is what we are given. Okay, and this is bounded above and below by some stuff, right? So if I divide this by x transpose x, let's also divide this by x transpose x. Then in the bottom, what can we get? This will be lambda 2, right, of the graph. And on the other side, which is the maximum value of the Rayleigh quotient, is lambda n. Do you agree? And so now let me bring the x transpose x out of the denominator. I'm going to take it out of the denominator. And I'm going to also remove this. So I have this is less or equal to lambda 2 times x transpose x. And this is greater equal to lambda n times x transpose x. Okay? So no matter what graph structure these differences corresponded to, right? If I give you only some differences, then there is some graph to go with it. I will get this inequality, right? I can bound this norm square above and below by the top eigenvalue and the second eigenvalue of the graph, okay? This is for the all ones graph. So if your graph is conformally rigid, it means that by adding weights to the graph, you cannot improve these bounds, right? I cannot make lambda 2 bigger or lambda n smaller. If I want to improve these bounds, I need to squeeze from both sides. And I'm not going to be able to do that if the graph is conformally rigid, because this bound that I got from the unweighted graph is the best you can do, okay? So people who do things like frame bounds and all care about this sort of stuff. They want to recover information by knowing like differences or, you know, it's like, for example, maybe a related example is oftentimes people measure the distances between atoms in a molecule in a lab, and you want to reconstruct the molecule. Okay, so you don't know the structure of the molecule, but you're able to measure differences. And from that, you want to say the shape of the molecule is this way. This is how the various atoms are aligned. And this is a very common type of problem. The other type of problem you have is there's something called sensor localization, okay? So this is when people want to understand, for example, the bottom of an ocean floor. Okay, so they'll throw these sensors into the ocean, and they have little emitters. They emit like little radio signals, and therefore you can measure, like one sensor sitting here at the bottom of the ocean can read a signal from somebody close to this person, okay? But they can't read signals from like far away sensors, but they can tell you like, okay, my sensor and that sensor are distanced this much apart. So we don't know where the sensors are. We're just dropping it from some airplane into the ocean floor. But you can read from the land, you can read these differences. You can read differences, okay? So now you want to locate the sensors physically so that you can map the bottom of the ocean floor, okay? I mean, this is also used for all kinds of applications. This is called sensor network localization, where you have differences and you want to reconstruct, okay? So conformal rigidity will tell you that you can't improve this, right? So these are graphs that have that type of property. Okay, maybe that's the only real application I will talk about. If you're interested, you can read our paper. There's a lot more stuff in there. So that is
More examples
of what?
conformity with it.
Yeah, oh yeah. So there are tons of examples, and I'm going to tell you in a minute. So actually, maybe you can guess one big class of conformally rigid graphs. So the key point is adding weight should not help you. Regular. No, regular is, yeah, some kind of transitivity. What? Close, close. Edge transitive, right? So if your graph is edge transitive, which means that every edge can be mapped to any other edge by a graph automorphism. That means all edges are essentially the same, right? Any edge can be sent to any other edge. So Kn, for example, complete graph is edge transitive. All edges have the same role, right? Up to relabeling of the vertices, Kn is the same, no matter what you do. K, yeah. Mm-hmm.
If you do not have the complete information, you cannot get extra, you cannot compute norm extra.
Yeah, you'll only get a bound on it. But these two numbers, I'm calculating from the all ones weight, right? So this number and this number is coming from the all ones weight. So you can ask, if I change the weights on the underlying graph, there's an underlying graph, right, that comes from knowing which ij's we know. Right? So you can ask, okay, can I change the weights on the underlying graph so that I can push this number down and this number up? Right? That's possible because we're just given these differences. That means we have given some graph, but nobody told you can only put weight 1 on it, right? We could put some other weights on it and hope that this will squeeze from both sides. Could happen. But I'm saying that if you're conformally rigid, it doesn't help to put weights. This is the best you can do.
So from the information of xi minus xj square, you get some bound on norm x square.
Correct.
But an upper bound.
Upper bound and a lower bound. Yeah, you'll know that it's within this range. Okay, I won't know exactly. For the complete graph, we knew.
You just have the upper bound and
That's right. But in things where if there is a graph that is not lower conformally rigid, then there will be some weight you can put here. You can weight the graph so that you will get lambda 2 of 1 times x transpose x is strictly less than lambda 2 of whatever weight you decided to put, x transpose x. Maybe if this weight is going to give you a bigger lambda 2 than the 1 weight, then you can make the bound better, right? That's what I'm trying to say. So you cannot improve these bounds if you have a lower conformally and upper conformally rigid graph. So that's one application. But there's a whole bunch of applications in the paper, and maybe I won't go there. But let's look at examples. So you agree that edge transitive should work? Okay. So examples. Yeah? That will also acquire some weights in it. That's correct. It'll change. That's true. So you have to have a trade-off. Yeah, that is true. You're right. Yeah. So the Laplacian will also slightly change. Right. So let's see. So what are some? So let me just quickly write down some examples without actually saying why they work. So edge transitive we expect will work. Right, because all the edges are the same really, so why would we, so there's no way that we will have to put different weights on different edges and try to increase lambda 2, okay? So
this is proved or we?
It's proved,
okay.
It's proved. And the proof is fairly simple. I don't know if we'll get to it, but.
This is both low, this is conformally rigid.
It's conformally rigid, okay? So these are conformally rigid. In fact, almost everything we know, I think, is just conformally rigid. So that's a class that's conformally rigid. And then maybe I'll give you a couple more examples that are conformally rigid. So if you're a distance regular graph, you're conformally rigid. What? No. Not all. Distance regular graphs are not all edge trans. Yeah, exactly. Yeah. So this is it. I'll explain what this means in a second. So this is inside a bigger class of graphs called one-walk regular graphs. Okay. So what does distance regular mean? It means that if you look at two vertices in the graph, let's say x and y, and the distance between them is something. So the distance in a graph is just the shortest path from one side to the other side, okay? So from x to y. So something is distance regular if the number of neighbors to X, so what's the definition? I forgot now.
Neighbors distance, distance.
Oh yeah, so the number of,
D minus 1 and D plus 1.
yeah, so the number of neighbors that are at distance I, let's say, to X, so there may be other nodes in the middle, and the number of neighbors that are, sorry, distance I to this one and distance J to this one. So if I want to count how many neighbors are there like this, okay, I pick two vertices, they have a distance, let's call that D, and I now want to count how many neighbors are distance I to this one and distance J to that one. That number only depends on I, J, and D, okay, that's what it means to be distance regular. So it only depends on these three numbers, okay, so it's also highly symmetric type of graphs. And then there's something called one walk regular, which is weaker. It is saying that if you pick two adjacent vertices, okay, and you play the same game, you look at the number of neighbors that are distance I to this and J to that, something like that. Well, I'll look up the definition, I'm sorry. But anyway, so they are also like this, okay. So I won't actually prove any of these results. I actually want to show you something else in the time that we have. But if you're interested, you can look at the proofs. So the proofs use some semi-definite programming, but more interestingly, they use spectral embeddings, which is the piece that I would like to show you, because I think it's very visual and you can understand what it means to be conformally rigid, okay? So there are some examples, we have some proofs, and there are also some, we now have a characterization of Cayley graphs that are conformally rigid. So not all Cayley graphs are conformally rigid, but there's a condition that they have to satisfy. So we have a kind of an if and only if condition for a Cayley graph to be conformally rigid. This is very big, okay?
So one walk regular are also conformally rigid?
They're conformally rigid. Right, so Cayley graphs, there is a necessary and sufficient condition. They're slightly different. They're not exactly if and only if, but there is a condition. Okay, so then in the open problems, there are several problems. Maybe the simplest one is if you look at circulant graphs. Do you know what they are? Circulant graphs. So circulants means that you start with the cycle, like for example, this is 1, 2, 3, 4, 5, 6, 7. And then I want to use circulants that have two generators. That means I decide to connect everything of distance A and everything of distance B. Okay, so for example, let's take the first distance to be 1. So I want to connect things at distance 1 from each other. So that means I'll get this outer cycle. That is the first distance. So let me give it 1. And then I'm also want to connect everything at distance 3, let's say. So 1 will be connected to 4. 4 will be connected to 7. And 7 will be connected to 3. And 3 will be connected to 6. And 6 will be connected to 2. And 2 will be connected to 5, and 5 will be connected back to 1. Okay, so this is called a circulant with these two numbers are called the generators of the circulant. Okay, so there are three parameters. There's n, which is the number of vertices. There are these two distances. You can put any number of distances, but let's just take two distances. Okay, so we don't know which circulants are conformally rigid. That's an open problem, okay? So maybe you can think about it. We have some examples in our papers. So we argue that we do know an infinite family that's conformally rigid. We do know an infinite family that is not conformally rigid. So some of them are not conformally rigid, but there's no complete characterization. So I think this is the easiest of all the problems on conformal rigidity. It may not be super easy. It has to involve some kind of number theory, right? Because circulants have this modular arithmetic going on. So it'll involve some kind of number theory, I think, the answer, analytic. I mean, sorry, just basic number theory, nothing complicated, hopefully. But it's tricky, okay? So if you're interested, we have two papers on conformal rigidity. Stefan and me have our first paper, and then there's another one with Joao Gouveia, two papers. And in both of them, in one of them, you see an infinite family that is not conformally rigid. I think if you use 1, 2, it is not conformally rigid. There's an infinite family. It starts with n equals 7 on, so 7, 8, and so on. And then in the second paper, we have an infinite family that is conformally rigid. Okay, so there are infinitely many circulants that are conformally rigid, but what's the complete theorem? There should be some theorem that only depends on n and these two numbers, right? So maybe these two numbers we call d1 and d2. These are the distances, so that's open. Good? You can put those if you think you need them in your theorem. At the moment, no. So you might say that if you don't have some extra condition on d1, d2, then it's going to behave in a certain way. So maybe look in the circulant literature and like take the most good definition. So you probably want it to be connected. You want it to be, I think there's some simple conditions that make sure it's connected. You're right, probably. Okay, so you can put whatever reasonable assumptions on this, and this is an open problem. Okay. All right, why don't we stop here, right? And then in the last session, I will show you how conformal rigidity is the same thing as finding certain types of spectral embeddings. So these can be conformally rigid only if the graph can be embedded in a very, very nice way. Okay? So I won't give any proofs of why these results work, but maybe that's not so enlightening anyway. But let's do the spectral embedding part that I think is very visual.